Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the micro bending losses and the Kerr effect and the intermodal dispersion. Let's start with the micro bending loss. So what's a micro bending loss? Let's first discuss with a diagram that at the time of manufacturing, when the core and the cladding have the very small bands, or it may be possible that due to the external force or the pressure, these bands may occur. When these bands occurs, then the light, the optical wave or the light will divert in the cladding. So that light is lost in form of radiation. So here we can see their power coupling to the higher order mode. So even it is possible that due to these microbands, these light propagating inside the core is change its pattern or the mode. So another form of the radiation loss in an optical waveguide results from the mode coupling caused by the random microbands of the optical fiber. Microbands are repetitive small scale fluctuation, as we have seen in the figure, in the radius of the curvature of the fiber axis. They are caused either of non-uniformities in the manufacturing of the fiber or by the non-uniform lateral pressure created during the cabling of the fiber. So it may be possible that during the cabling these microbands are created. The later effect is often referred to as the cabling or the packaging loss. So at the time of cabling, if the microbands are produced, then these are known as the cabling or the packaging losses. An increase in attenuation results from the microbanding because the fiber curvature causes repetitive coupling of energy between the guide modes and the leaky or the non-guided modes in the fiber. So one method of minimizing microbanding losses is by extending a compressible jacket. So we can use a compressible jacket in the core and cladding such that the deformation cannot be formed in a cladding or the core over the fiber, which is deformed due to the external force, but fiber stays straight. So if we make a compressible jacket, or this core and cladding is holded in a compressible jacket, now these compressible jacket may compress by the external pressure and remaining this fiber straight. So this force we can calculate that how much force that a compressible jacket can withstand, that can be calculated with the formula that is F in alpha, that is 1 plus pi delta square B by A EF by EJ, where this EJ and EF are the Young's modulus of the jacket and fiber respectively. The Young's modulus of the common jacket material ranges from 20 to 500 megapascals, and the Young modulus of the silica glass is 65 gigapascals. So as we can see in this diagram, here we have applied the external force, and this is the compressible jacket. Now due to this force, this compressible jacket is compressed while the fiber is having the macro bands, not the micro bands. So this compressible jacket extruded over a fiber reduces the microbanding results from the external forces. Now the next important topic in optical communication is the Kerr effect. Now we know that the light is propagating inside the fiber core. Now when the refractive index of the core changes, then we are having these effects that is known as the Kerr effect. So the refractive index N of many optical materials has a weak dependence on the optical intensity, that is I. that is equal to the optical power per effective area in the fiber given by, that is n equals to n naught plus n2I, that is equals to n naught plus n2, and this intensity is nothing but the optical power divided by the effective area, where n naught is the ordinary refractive index of the material and n2 is the non-linear index coefficient. So in silica, the factor n2 varies from 2.2 to 3.4 into 10 to the power minus 8 micrometer square per watt, and the non-linearity in the refractive index is known as the Kerr non-linearity. This non-linearity produces a carrier-induced phase modulation. So this is the important term, means this is happening a self-modulation, because we are saying that carrier-induced. So here carrier in optical communication is simply the optical light of the propagating signal, that is known as or called as the Kerr effect. So this effect is known as the Kerr effect. So in single wavelength link, this gives rise to the self-phase modulation, that is SPM, which converts optical power fluctuations in a propagating light wave to spurious phase fluctuation in the same wave. So as we can see in the diagram, we are having the front of the pulse and the back of the pulse, and we are on the y-axis we are having the intensity of the light, and in the second figure we are having the frequency. So frequency is varying higher and lower. Now due to this, the intensity, as the intensity is decreasing, the frequency will increase or it will decrease depending on the pattern change or the intensity change. So this is a phenomenological description of the spectral broadening of the pulse due to the self-phase modulation. So next important topic is the dispersion. So dispersion is simply the broadening of the pulses. So we are using the digital pulses to transmit our data in optical communication. So when these pulses, for example, we are having this rectangular pulse as 1 in binary and 0 is represented by 0 volt if we are using an NRZ signaling. Now when these pulses are fed to the fiber at the receiver side, these pulses are broadened like this. Now due to this broadening, if we are transmitting a pulses or the pattern, these pulses may overlap with the consecutive pulses. Now this overlapping of the pulses will cause inter-symbol interference, that is ISI. So the dispersion of the transmitted optical signal causes distortion for both digital and analog transmission along the optical fibers. Optical fiber transmission, which involves the digital communication. So here we have the digital communication as in the form of ASK, FSK or PSK, that is phase shift keying. So it may be amplitude shift keying, frequency shift keying or phase shift keying. Then the dispersion mechanism with the fiber cause broadening of the transmitted pulses, as we can see in this. Here this effect can be observed where we have the broadening and the overlapping of the pulses causing the inter-symbol interference. Broadening of the transmitted light signal as they travel along the channel, and it may be observed that each pulse broadens and overlaps with its neighbors, eventually becoming indistinguishable at the receiver input. So this is known as, or this effect is known as the inter-symbol interference. The effect or the error rate is also a function of the signal attenuation on the link and the subsequent signal to noise ratio at the receiver. So signal dispersion alone limits the maximum possible bandwidth attainable with a particular optical fiber to the point wherein individual symbols can no longer be distinguished. So let's see this diagram. Here it is explained. where we have the data that is 1, 0, 1, 1, and we are having the pulses that is very narrow width pulses. Now, when these pulses are transmitted over a distance of the optical fiber, let's say L1 is the distance, we can see that after some delay, we are receiving these pulses that is 1, 0, 1, 1, but here the broadening of the pulses may be observed. Now, due to this broadening that is 1, 0, 1, 1, there is an overlapping of the pulse, and here we can see that this is nothing but ISI, that is intersymbol interference. In the next case, when the distance, it is traveling more distance, that is L2, where L2 is greater than L1, then we can see there is more broadening of the pulses. When we have the more broadening, then even this pulse, that is the first pulse, it may overlap with the third pulse, that is 1. Now here we can say that there is more intersymbol interference between the first pulse and the third pulse, and this may cause the error at the receiver side. So this is the figure for the illustration using the digital bit pattern 1011 of the broadening of light pulses. They are transmitted along a fiber, that is the fiber input, the fiber output at a distance L1, and the fiber output at a distance L2, which is greater than L1. So for no overlapping of light pulses down on an optical fiber link, the digital bit rate, that is BT, must be less than the reciprocal of the broadened, that is through dispersion, pulse duration, that is 2 tau, where tau is nothing but the broadening of the pulses. If we have the bit duration that is given by TB and this pulse is broadened by the tau, then this broadening is given by tau. So this assumes that the pulse broadening due to the dispersion on the channel is tau, which dictates the input pulse duration, which is also tau. Hence, the equation gives the conservative estimate of the maximum bit rate that may be obtained on an optical fiber link is given by 1 by 2 tau. Another more accurate estimate of the maximum bit rate for an optical channel with dispersive may be obtained by considering the light pulses and the output to have the Gaussian shape with an RMS width of tau. So we can calculate this analysis follows the existence of certain amount of signal overlap on the channel while avoiding any SNR penalty which occurs when ISI becomes pronounced, and the maximum bit rate is given approximately by, that is BT, can be calculated as approximately equals to 0.2 by sigma, that is in units is bits per second. So here the effect of dispersion for different fibers, that is a multi-mode step index fiber, multi-mode graded index fiber, and single mode step index fiber. As we can see, all these fibers are fed with a narrow width pulses and it is traveling through the fiber, and at the receiver side we are getting the dispersion effect, means the pulse broadening we can see. The maximum broadening we can observe in a multi-mode step index fiber, then the intermediate broadening can be observed in multi-mode graded index fiber, and very less broadening we can observe in the single mode step index fiber. So this figure shows a multi-mode step index fiber, multi-mode graded index fiber, and single mode step index fiber, and illustrating the pulse broadening due to the intermodal dispersion in each fiber type. So this is the explanation. The figure shows the three common optical fiber structures, namely multi-mode step index, multi-mode graded index, and single mode step index, while diagrammatically illustrating the respective pulse broadening associated with each fiber type. it may be observed that the multimode step index fiber exhibits the greatest dispersion of the transmitted light pulse, and the multimode graded index fiber gives a considerably improved performance. Finally, the single mode fiber gives the minimum pulse broadening, and this is capable of the greatest transmission bandwidth, which are currently in gigahertz range, whereas the transmission via multi-mode step index fiber is usually limited to the bandwidth of few tens of megahertz. The amount of pulse broadening is dependent upon the distance and the pulse travel within the fiber, and hence for a given optical fiber link, the restriction on the usable bandwidth is dictated by the distance and the regenerative repeater. So, the measurement of the dispersive properties of optical fiber is usually stated as the pulse broadening in time over the unit length of the fiber, that is in nanoseconds per kilometer, and the number of the optical signal pulses which may be transmitted in a given period, and therefore the information carrying capacity of the fiber is restricted by the amount of pulse dispersion per unit length, and in the absence of mode coupling or filtering, the pulse broadening increases linearly with the fiber length, and thus the bandwidth is inversely proportional to the distance. So, this leads to the adoption of more useful parameter for the information carrying capacity of an optical fiber, which is known as the bandwidth length product, that is B optimum multiplied by length, and the typical best bandwidth length product for the three fibers are 20 megahertz, 1 gigahertz and 100 gigahertz kilometer. So, for an multi-mode step index, multi-mode graded index and single mode step index fiber respectively. So, there is one numerical based on the calculation that a multi-mode graded index fiber exhibits the total pulse broadening that is given in terms of 0.1 microseconds over a distance of 15 kilometers. So, we have to estimate the maximum possible bandwidth on the link assuming no inter-symbol interference. So, without ISI, we have to calculate the maximum possible bandwidth, the pulse dispersion per unit length, then the second point, and the third one is the bandwidth length product for the fiber. So, the maximum possible bandwidth can be calculated as, that is 1 by 2 tau, as we have discussed in the previous slide, that is given by 1 by 2 tau. Using this formula, substituting the value, we are having the 0.1 microsecond. So, 2 multiplied by 0.1, we are getting 0.2 into 10 to the power minus 6. So, we are getting a 5 gigahertz, 5 megahertz for the possible optical bandwidth. So, now the second part is the pulse dispersion per unit length. So, the pulse dispersion per unit length can be calculated as, that is the tau divided by the length, that is length is given by 15 kilometers. So, tau divided by L. So, we are getting the dispersion, it is 6.67 nanoseconds per kilometer. Now, the third part, that is the bandwidth length product for the fiber. So, the bandwidth length product, so bandwidth we have calculated as 5 megahertz multiplied by for 15 kilometer. So, we are having 75 megahertz kilometer. So, the alternate solution, it can be simply multiplied. So, 1 by 2 tau multiplied by kilometer, that is length, we are getting 75 megahertz kilometer. Now, the classification of dispersion. So, dispersion can be classified as the intramodal dispersion and the intermodal dispersion, and the intramodal dispersion can be further classified as the material dispersion and the waveguide dispersion. In this lecture, we are going to cover about the intramodal dispersion. So, intramodal dispersion is also known as the chromatic dispersion. So, it may occur in all types of the optical fiber, results from the finite spectral line width. So, this is an important keyword of the optical sources. So optical sources are nothing but LED and laser. So optical sources do not emit just a single frequency but a band of frequencies. In the case for the LED, it is a significant percentage. Then there may be propagation delay difference between the spectral components of the transmitted signal. So this causes the broadening of the transmitted mode. Modes means nothing but the patterns, and hence the intramodal dispersion. So the delay difference may be caused by the dispersive properties of the waveguide material. So it may be due to the waveguide material, whatever dielectric we are using to make our optical fiber, and also the guidance effect within the fiber structure, or it is known as the waveguide dispersion. So there are two types, that is waveguide and material dispersion. So let's start with the material dispersion first. So the pulse broadening due to the material dispersion results from the different group velocities of the various spectral components launched into the fiber from the optical source. It occurs when the phase velocity of a plane wave propagating in the dielectric medium varies non-linearly with wavelength, and a material is said to exhibit material dispersion when the second differential of the refractive index with respect to wavelength is not 0, that is d2n by d lambda square, which is not equals to 0, because we have studied that the phase velocity and the group velocity, that is group velocity, is given by c by the ng, and the phase velocity Vp is given by c by n. So the group index is having this term, that is d2n by d lambda square, which is not equals to 0. So the pulse spread due to the material dispersion may be obtained by considering the group delay. So here we have to consider the group delay, that is tau g in the optical fiber, which is the reciprocal of the group velocity Vg, that is the c by ng, that is group index defined by the equations. So we have the group delay that is given by tau g, that is d beta by d omega, which is given by 1 by c n1 minus lambda d n1 by d lambda square, where n1 is the refractive index of the core material. The pulse delay tau m due to the material dispersion in a length, that is L, is therefore given by tau m. Tau m equals to L by C n1 minus lambda d n1 by d lambda. So for a source with RMS spectral width, that is sigma lambda, and a mean wavelength lambda, the RMS pulse broadening due to the material dispersion, that is sigma m, may be obtained from the expression of equation in a Taylor series with lambda. So here we have the sigma m, that is given by sigma lambda d tau m by d lambda, sigma lambda d2 square tau m by d lambda square, and so on. So as the first term in the equation usually dominates, especially for the source operating at 0.8 to 0.9 micrometer of wavelength range, and the sigma m for the material dispersion we can calculate, that is approximately equals to sigma lambda d tau m, that is the delay, material delay by d lambda. So hence the pulse spread may be evaluated by considering the dependencies of tau m on lambda, where from the equation we are getting, by differentiating with respect to lambda, we are getting lambda into L by C d2 n1 by d lambda square. So therefore, substituting the expression, the RMS pulse broadening due to the material dispersion is given by, that is sigma m, that is equals to sigma lambda L by C lambda d2 n1 by d lambda square. The material dispersion for the optical fiber is sometimes quoted as the value for d lambda 2, that is d2 n1 by d lambda, or simply d2 n1 by d lambda square. However, it may be given in terms of the material dispersion, that is m, that is given by 1 by L d tau m by d lambda, that is nothing but L lambda by C d2n1 by d lambda square, and the unit is picoseconds nanometer per kilometer. So here we can see the material dispersion, how it is varying with the wavelength. So wavelength is varying from 0.6 micrometer to 2.2 micrometers. So due to the material dispersion, it is varying in picoseconds, so it is decreasing with respect to the wavelength. As the wavelength increases, it decays exponentially, and we are having the region of the negligible dispersion material. So here we can see we are having the negligible material. Here we have the positive dispersion, and this region covers the negative dispersion. So negative dispersion means the pulse narrowing, and the positive dispersion means pulse broadening. So it may be observed that the material dispersion tends to 0 in longer wavelength region, around 1.3 micrometer, for when we are using the pure silica. So this provides an additional incentive other than the low attenuation for operating at longer wavelengths, where the material dispersion may be minimized. The use of the injection laser with narrow spectral width rather than LED as an optical source leads to the substantial reduction in the pulse broadening due to the material dispersion in the shorter wavelength region. So there's one numerical, so let's solve this. So a glass fiber exhibits a material dispersion given by d lambda square d2n1 by d lambda square of 0.025. This value is given. Determine the material dispersion parameter at a wavelength. So lambda is also given, that is 0.85 micrometers, and estimate the RMS pulse broadening per kilometer for a good LED source with an RMS spectral width of 20 nanometers at this wavelength. So the material dispersion parameter may be obtained from, so M can be calculated using this formula which we have seen, that is lambda by C d2n1 by d lambda square. The same formula we are using, that is M equals to lambda by C d2n1 by d lambda square. Further simplifying and substituting the value, we are getting 98.1 picoseconds per nanometer per kilometer. The RMS pulse broadening is given by, that is sigma M, that is equals to, that is sigma lambda L by C lambda d2n by d lambda. So for material dispersion parameter, that is equals to sigma lambda L into M. Substituting the value, we are getting the material dispersion parameter as 1.96 nanoseconds per kilometer. So there's one more numerical. So estimate the RMS pulse broadening per kilometer for the fiber when the optical source used in the injection laser with a relative spectral width, that is sigma lambda by lambda of, so this value is 0.0012, and we are having a wavelength of 0.85. So solving it, we are getting a sigma lambda as 1.02 nanometers, and using the material dispersion parameter and the formula, we are getting sigma lambda as 0.1 nanoseconds per kilometer. So in the second part, that is the waveguide dispersion. The waveguiding of the fiber may also create the chromatic dispersion. So this results from the variation in the group velocity. So the cause of the waveguide dispersion is a group velocity with a wavelength for a particular mode. Considering the ray theory approach, it is equivalent to the angle between the ray and the fiber axis varying with a wavelength, which subsequently leads to the variation of the transmission times for the ray, and hence we are having the dispersion, that is the pulse broadening. For the single mode where the propagation constant is beta and the fiber exhibits the waveguide dispersion when d2 beta by d lambda square is not equals to 0. So for multimode fiber where the majority of modes propagate far away from the cutoff and are almost free of the waveguide dispersion and is generally negligible when compared with the material dispersion, which is having the order of 0.1 to 0.2 nanoseconds per kilometer. So with a single mode fiber where the effect of the different dispersion mechanisms are not easy to separate, and the waveguide dispersion may be significant. So in this video lecture, we have discussed about the microbending losses, the Kerr effect, and the intramodal dispersion. So in intramodal dispersion, we have discussed about the material dispersion and the waveguide dispersion. So here we are going to stop the lecture. Thank you.